Thank you for the invitation to be here. It's a great opportunity. It's quite unique that you walk in the street and then you find a wall with names of mathematicians. There are not many cities like that. Anyway, it's a pleasure to be here. The reason I wanted to put this up, if you look up there, that's a web address of my homepage. And if you scroll down to this location, down here, and you click it, you'll find my lecture notes, a copy of the lecture notes for this course. So you can all, if you like, download it, or you can copy the direct link from up there. And this covers more or less the material I want to talk about here. Okay, so I'm going to switch back to this. And in fact, I plan not to use too much the computer, but just to tell you a little bit about the plan for these lectures. So the very first lecture, and maybe also tomorrow, is going to be very elementary and very slow. Actually, the whole thing is going to be rather elementary. I'm going to revisit a very... It doesn't work?
No, that's for the recording, and this one is for the...
Okay. And if I shout, that's not enough? People don't hear me in the back? No. And now you hear me? Yeah, but okay.
We'll fix it next time.
Okay. So I'm going to start off with discussing branching random walks. This is a very classical topic. Early works related to branching Brownian motions go back to the 30s, although it was not framed in that language. So I'll describe in a few minutes what I mean by that. And then we'll discuss all the basics, namely, how do you obtain a law of large numbers for branching random walk? What is the relation between this law of large numbers and independent walks? What happens for independent walks? And some techniques, and in fact, I will be very lowbrow here and discuss the most elementary techniques that you can use in order to get that. There are quite more sophisticated treatments now. Then I'll show you some argument that is maybe not that well known and I think should deserve to be known better, which is essentially saying that if you can show something about means, then you can show something about fluctuations. So I call it tightness, but it's actually something of the order, if you know certain means, you can control fluctuations. And then we'll see how to actually evaluate the corrections to the law of large numbers, which will play a lot of an important role later. So that's the beginning. And then I'll tell you about some recent developments related to time varying profiles for branching random walks, and there are some surprises there. In particular, some phase transitions will occur. And the rest of the talks, or probably the last two talks, will be devoted to the Gaussian free field, and specifically to the two-dimensional Gaussian free field, which a priori does not seem related to branching random walk, but we'll see that there is a deep connection between the two objects. So I'll define what I mean by that. I'll run you through some of the basic tools of Gaussian processes theory. And then we'll essentially repeat what we did for branching random walks. Namely, we'll discuss law of large numbers. We'll see how to adapt this means imply fluctuation argument. We'll see how to then control the expectations that are needed. And we'll do the analysis of the appropriate modified branching random walk that appear in the analysis. Finally, I hope I'll have time, and if I'll have time, I'll devote maybe most of the last lecture to some extensions of these results, and in particular, how all these are related to cover time for random walks on graphs, and in particular on Z2. and related topics of that nature. So that's the plan for these 4 lectures. And let me just put this slide, and then I'll switch to the blackboard. So what are branching random walks? So for me, the model is the following. We have some tree which throughout these lectures is always going to be a simple k-ary, actually binary for today and tomorrow, tree with a root. And just to fix notation, I'll denote by v the distance of a vertex from the root. dv is a degree, which we will take now constant, except for at the root, where it is. So for in the binary case, the root will have degree 2. Everything else will have degree 3. I'll denote by dn the nth generation, so all the particles at distance n from the root. And I'll denote by O connects to V all the vertices or all the edges along the geodesic connecting O and V. And now what is a model? We put on each edge a random variable called that we denote by xe. And those are IID with a certain law mu, which for the purpose of my lectures, you can right now think all the time Gaussian. So just think of mu as being Gaussian normal 0, 1. And then the value of the branching random walk at vertex V is simply the sum of this random variable along the geodesic connecting O to V. Okay, so that's the value at V. And our main concern, by the way, I'm talking here about, maybe I should have emphasized it, I'm talking here about one-dimensional branching random walks. So the increments take value in R. Many of the things I'm talking about could be discussed in higher dimension also, and it is interesting to do that, but my focus is on the one-dimensional case, which is the most studied one and actually has most of the key to other treatments. Then we will be interested in particular, because it's one-dimensional, we can talk about the maximal displacement. And it's clear what it means. It's just the maximum over all variables at generation n of the value of the walk at n. Okay? And finally, the assumptions for this lecture is, first of all, as I said, we will always be discussing the binary or 4-ary tree. You should keep in mind that almost everything that I say goes over to the case of Galton-Watson trees and other models. But again, my goal is not the most generality, but actually to show you some of the basic principles. So we are in a binary tree or in a regular tree. And then we assume that mu has super exponential tails, which means that all exponential moments are finite. Okay? And just keep in mind this notation here, this lambda. So this lambda here is a moment generating function associated with the increment xe. And as I said, the tree, and that's it. Okay, so I think I'm going to switch here to the blackboard, and we can forget about that. Is this the eraser? This is to erase? This? This?
Yeah, well, there's dry erase, there's also a wet erase.
No, the dry. Yeah, okay. That looks more too sophisticated. Okay, so remember that SV is just the sum of XE. And MN is the maximum of SV, V in dN. Is that big enough in the back there? Is my handwriting big enough? Yeah? Yeah, no? Yeah, you can see that. Okay, good. So the first step is a law of large numbers that we would like to be able to deduce. So the first question is, what can we say about Mn? How does it behave? So let's do some preliminary computations. So first of all, how does SV behave? So SV is a sum of independent random variables. As I said, I'm going to take this to be normal 0, 1. So in this case, SV is a very, you don't even need a central limit theorem to know that SV is just Gaussian with variance n. And therefore, SV is of the order of square root n. Okay, so that's a typical value for one independent walk. I didn't emphasize that, but I hope that it was clear why this is called branching random walk. Maybe I should have, I'm sorry, I should have said that before. It's called branching random walk because if you start with a particle here that branches in two, and each of the new particles is doing an increment, an independent Gaussian increment, and then each particle branches again and does a new increment, etc., what you see at time n is the increments of this collection of particles alive at time n. Okay, so that's the reason for the name. It's true that in the way I defined it, you didn't quite see that. Anyway, so a typical particle is at square root n, but we are asking about the maximum. So what is a back of envelope computation? Well, we have 2 to the n particles. And on the other hand, we know that SV is normal 0, n. And therefore, the probability that SV is roughly nx is e to the minus nx square divided by 2n, which is e to the minus nx square over 2. Okay? And therefore, one thing is clear. If 2 to the power n times e to the minus nx square over 2, if I choose an x such that this quantity goes to 0, then there will not be particles at that distance. Because what is this quantity? This is exactly the expected value of the sum of the indicator that S, so this is V in the n, that SV is greater or is roughly nx. Actually, this is also true. So this expected value is roughly of this order. And if I choose an x which is too large such that this goes to 0, then this will go to 0, and this is of course larger than the probability that there is a particle larger than nx. Okay? So in particular, just from this type of computation, I can get easily an upper bound on the distance of the rightmost particle. And every time I do such a computation, I will refer to it as a first moment computation. And the reason it is a first moment computation is that I'm computing the first moment of a certain random variable. In this case, the random variable is this sum of indicators. Okay? So this is rather clear, and so the conclusion is from here that if x is greater than whatever comes from here, which is probably square root 2 log 2, Mn is smaller than Nx with high probability. And in this case, high probability just means with exponentially 1 minus an exponentially small probability. Okay? Okay. So the big question is, how can we actually say something better about Mn? So before we go into that, what is the difficulty in the model? The difficulty in the model is that particles are correlated. So for example, if you go on the tree, it's clear that the particle down here and the particle down here are very correlated. In fact, they only depend by one increment of the random walk. The only difference is in one increment of the random walk. Therefore, with very overwhelming probability, this particle and that particle are very close together. And before we do more detailed computation for that model, let's do an undergraduate exercise, which is to see what happens in the case of independent particles. So suppose that, so let me call it, do you see what I'm writing on this blackboard here? Yes, no? Okay. So D2 is going to be independent particles. So by this I mean, suppose I have two, so that's a new model, suppose I have 2 to the n particles, and each is normal 0, 1, 0, n. So the marginal of each particle is the same as in the original picture, but now they are all independent. Okay? So in this case, we can actually compute what is the probability that there exists a V such that SV is greater than Nx. Okay, so these particles are indexed by that. Well, this is 1 minus P that SV is greater than Nx to the power 2 to the power n. Okay, because they are independent. And if now I substitute the asymptotics, in fact, I have to substitute precise asymptotics. Let me do that here. So now we are going to use an asymptotic that is slightly more accurate than that. Namely, that the probability that SV is greater than Nx minus An. We will see the reason for that in a second. This is roughly e to the minus so this is a local limit, but in this case it's just the asymptotics of the Gaussian density. Note that if I were dealing with other random variables, I would get similar results. The only difference would have been the function that comes in here. It would not necessarily be quadratic. It would be actually the large deviation rate function. But if you don't know what that is, it's not important because we are dealing with Gaussian. So in the Gaussian case, that's all you would get here. And if you now, so let me rewrite that as C e to the minus nx squared over 2 that we had before, e to the plus x an, and then e to the minus 1/2 log n. Let me write it like that. Okay? And an, we are going to take an such that an is much, much smaller than n, so that an squared divided by n is not going to play any role. Okay, so this implies that an squared divided by n goes to 0. And therefore is not going to play any role. Okay, so when we substitute this, and we carry the little calculus exercise that comes into the game, what we will discover, if we take the same x that we took here, that I'm now going to call x star. So if we now substitute x equal to x star and push it into here, what we will see is that, so let me call this P star. What we will get is that if we take an to be 1/2 log n plus y, then just substituting and doing the computation, this 1/2 log n is going just to kill, 1/2x star log n. If we just substitute and do the computation, what we will find is that Pn star converges as n goes to infinity to e to the minus c, e to the minus y it's going to be, e to the minus y over 2, I believe. It should have been y, so, sorry. No, it's 1/2. That's okay. Yeah, it's e to the minus y. Thank you. Sorry. So that will be the statement. So the statement would be that we converge to that, and then you recognize it as one of the types of extreme distribution, in this case, the Gumbel distribution. So we know everything about the random variable. In particular, in this independent case, we see that the maximum of SV, let's call it the maximum of SV, where V, and those are independent. So let me put here a tilde to remind us that this is an independent case. This behaves like n, so x star n minus 1/2 x star log n plus y plus order 1, and this order 1 we know exactly the fluctuations of it. Okay? In particular, SV tilde, this maximum, so mn tilde divided by n converges to x star. And this convergence is in probability, but in fact, if you follow the proof, you see that you can make it easily into an almost sure convergence because we have exponential decay of probabilities all over the place. So this is a baby computation for the independent case. And now we need to see how much of that can be salvaged for the branching random walk. So the first step, our goal will be to get statements like that for branching random walk. And in fact, this is the ideal statement that we would shoot for eventually, but that I will not cover in the lecture. Namely, eventually we would like also to be able to say something about limit laws. But my goal is actually to get statements like that without discussing limit laws. Okay? So this involves several steps. So the first step is the law of large number, which is mn tilde over n goes to x star. So So a statement like that I'll refer to as law of large numbers. And then the second step is going to be the deviation from law of large numbers. So in this case, it's logarithmic. And then order 1 fluctuations. So this deviation, I actually deviation of the mean. Okay? So those are the 3 steps we want to do. And we want to do in the case of law of large numbers. So let's now go back to our branching random walk model, to Mn, not to Mn tilde. And we would like to discuss this, but for Mn. And 1/2 of this statement we already did. Namely, if I go back to this computation, we already show that so from first moment of Zn, which is the sum of the indicator that SV is, say, larger than Nx. So let's now be precise. So suppose I take this random variable and I apply the computation I did here. Because of my epsilon here, I see that the expectation of Zn decays exponentially to 0. So from this, I easily deduce that Mn over n is less than x star, less than or equal to x star, with high probability, actually with overwhelming probability, so you can make it into a lim sup statement. Okay? So we need a complementary lower bound. Now, in the baby problem, how did we get the complementary lower bound? We actually computed the probability. We wrote an expression for the probability and we computed it, and this we have no hope of doing it. It's too complicated. But there is a different technique which could work and would still work in the case of independent random variables. Namely, I could now define a new random variable. Let's call it Zn minus. And I'll call Zn minus to be the sum So here I do expect to have, if a law of large number would be true, then I do expect a lot of this, or some of these particles to be smaller than, to be larger than nx star minus epsilon. So the expectation of Zn minus goes to infinity. That's the same computation as we did here. You just plug in x star minus epsilon. This goes to infinity. So what you would like to be able to say is if the expectation of Zn minus squared, if this is not too large, namely the variance is not too big, then the mean going to infinity and the control on the variance should say that the random variable itself is with high probability positive. And in fact, all you need for that, so if this is small, we are okay. And what I mean by small is simply an application of Cauchy-Schwarz. Namely, the probability that Zn tilde is greater than or equal to 1 is at least this quantity by Cauchy-Schwarz. And so if I am able to control this difference, then, not the n tilde, this is the n minus. Sorry. The n minus. So if I'm able to compute both first moment and second moment and somehow compare them, then I'll have a lower bound and I'll be happy. Now, if you repeat the computation we did for the independent case, this works for independent. And the reason it works for the independent case is that it's very easy to compute it, because when you compute the second moment, what comes into the computation of the second moment is just the correlation between two particles. In the independent case, there is no correlation. So the dominant term in the computation of the expectation of Zn minus square is simply the first moment square. And then there is a diagonal element which comes from choosing the same V when you compute the square. And this one is actually, you can check that it's negligible. So this works for the independent case, and you have this will imply the law of large numbers, namely will imply that this is positive with overwhelming probability, and you're done. Okay. But if you now did the computation for the branching random walk, it's also not too hard. Why? Well, what is the expectation of Zn minus squared? Well, this is a sum over U and V of the probability that SV is greater than Nx star minus epsilon, and also Su. That's the second moment. Now, what does it mean on the tree? It means that we take two vertices, one vertex U here, one other vertex V here, that have split at some point in their history. And we ask, what is the probability that both this guy is large and this guy is large? But those are all Gaussians here. So we really have three random variables in play. We have one random variable which, I don't know, let's call it A. And then we have B1 and B2. B1, A, and B2 are all independent. So what is written here is just a Gaussian computation. What is the probability that both A plus B1 is large and A plus B2 is large? Okay, so this is probability that A plus B1 is greater than that, and A plus B2 is greater than the same object. Yes?
The square inside of the parentheses.
It is. So what? Yeah, so it's the second moment of this random variable. Okay, so that's easy to compute. And if you do it, which I will not do on the blackboard, then you discover that the second moment blows up. So this method does not work. So second, the expectation, so this quantity, let's call it star, star goes to infinity as n goes to infinity. So you can't do that. Now, before we discuss how, sorry?
To zero. It goes to zero.
This one goes to 0, yes. The second, yeah. Thank you. So, why is that? What is going on here? And can we try to fix this? So, of course, many people in this audience know what you do, but still, I promise to bore all the experts, so I'm going to do it anyway. And you ask yourself, what is going on? And you realize the following. If I didn't have the particle V, if I only had the particle U, and I asked the particle U, the value here to be large, suppose that this is halfway. So suppose that this distance here is n half, and this distance here is n half. What is a typical value of S at this point? So conditioned on having a high value here. Namely, what is the probability? What is the distribution of A conditioned on A plus B is greater than what was written here? Okay? Well, this is a jointly Gaussian vector. So in order to know the conditional distribution, I have to compute the conditional mean and the conditional variance. The conditional mean, what will it be? Any guess? Quick guess? We are at halfway through. So this value is something. So what is it if I condition to be that large? What is it in the middle of the way? It's half that value. So the conditional mean is just a linear functional of the conditioning. It will be just half of the value here. The variance will be of the same order, will be of order n still. Okay? So that's if I only condition on this point to be large. Now, suppose I condition not just on u to be large, but on both u and v being large. What will happen to this midpoint? So again, the typical behavior when I only conditioned on u being large is to be halfway up in the midpoint. If I condition on both u and v to be large, turns out, and it's not very hard to convince yourself, that this point will climb higher. Why? Because you pay, for this increment, you pay only once in terms of probability, whereas here you pay twice. So it's a little exercise, a little calculus exercise to compute the conditional expectation of this midpoint given these two values. And you'll discover that it's not n half, but it's some constant times n, where this constant is larger than 1/2. Which means that conditioning both these points to be atypical has led to an atypical behavior in the midpoint, atypical even under the event that you conditioned one point. Okay? So that's the reason why this quantity explodes, but it also gives you a recipe how to fix it. Namely, if I know that conditioning on this guy to be high, the typical value here is going to be half whatever I conditioned here, why don't I put into this event, into the event here, this extra information? When I compute the first moment, it will not cost me anything, because this is anyway the typical behavior. But it will reduce the variance. It will modify the probability and make it smaller. The second moment will become smaller. Okay? So this I call a modified second moment method. And it's very, very common. And I'm sure that a good part of the audience has already seen such computations. But anyway. So now we define the event AV to be the event that S, we would like, I'm going to do several steps, so I'm not yet defining the right event, but what we want that SV is greater than n x star minus epsilon, and I want to write here typical behavior. This is what I would like to do. So we have seen one way of saying typical. What was the one way? To say that at the midpoint, it should be roughly at height, half the height. Okay? But that is not going to help me if I'm going now to consider u and v like this, which are at a quarter of the distance. So somehow my extra information of typical should not just be at a fixed intermediate time, but at all times. So for doing that, we just define SV of t to be the sum from I equal 1 up to nt of S of x. Actually, let me write it differently. E in 0 connecting V, and E is smaller than nt of xe. So this is now the partial sum along the ray connecting 0 V of the increments. Okay, so that defined for me a process, if you want, a Gaussian process, which is a partial sum of random walks. Okay? And now I have a guess. What does typical mean? Namely, instead of typical, I should write here that S, instead of this event, I should say maybe that SV of t minus nt x star minus epsilon should be small. And here maybe small means epsilon n. Or, I don't know, delta n. Which is to say that you more or less follow the straight line along the path. Okay? Now, in the Gaussian case, what is this process, SV of t? It's just a partial sum of random walks. So what does it converge to as a process? It converges to a Brownian motion. Now, of course, you're conditioning on a rare event. So what I'm saying now should be taken with a grain of salt. But if you take a Brownian motion, you take the limit process, and you condition it to be at a high level, what do you get? You get a straight line plus a Brownian motion again, plus a Brownian bridge, in fact. And then the behavior of the Brownian bridge is that its fluctuations are bounded by square root n. And therefore, delta n is much larger than the fluctuations. So this is, we expect it to be a typical event. And in order to do that, we need a general statement that allows us to claim something like that. And this comes under the names of Varadhan and Mogulski. And this is actually a large deviation statement. Namely, what you can check is the following theorem. So, and the theorem is that if we forget about this, because this part is already included in that event, or at least if you modify a little bit the epsilons and the deltas, so if you just look at that event, then 1 over n log of the probability of AV, this is going to be minus x star minus epsilon square over 2. So this event decays exponentially, and it decays exponentially in the same rate that just this guy decayed. Okay, and I wrote here, of course, for the Gaussian case, you don't really need Varadhan and Mogulski, but this is true in much greater generality. In fact, under the conditions I stated in the beginning, namely that the increments have all exponential moments finite, this statement is true. Okay? Now, once you have that, you can carry out the second moment method. And when you do that, okay, so now you carry the second moment method. So yeah, why don't I do it here? So carry out and what you find is that the expectation of Zn, so this now Zn is not that event, but we define, maybe I should write it here. So we define Zn epsilon is just the sum of the indicator of AV. And when you carry out the second moment method, you discover what do you discover? What do you want? You want this to go to 1, right? Unfortunately, it doesn't. So what you find is that this blows up like that. Because remember, all we could do in this computation is compute exponential rates. So we have the exponents up to a little error, which has to do with all the epsilons in the game. So we cannot hope really to compute precisely the second moment and the first moment and compare them, because we will make errors that have to do with this limit. And these errors will accumulate exponential errors. So we will get something of that type. Okay? So it seems that this doesn't really, and again I'm doing my infinity versus 0 switch. So actually that's what you get. And that doesn't seem to be good enough. Because you want to show that the probability goes to 1. And does not go to 0. So what is the conclusion, however, from that? The conclusion from that is that the probability that Zn epsilon is greater than or equal to 1 is greater than e to the minus c of epsilon times n, and this c of epsilon goes to 0 with epsilon. But the order of the limits is that you first take n to infinities and epsilon. So this is not quite enough, but we're almost done. Why? Because we're almost done here because now we remember that we are on the tree. So there is, after all, some independence present on the tree that we have exploited, but only partially. We have exploited the independence in computing the second moment. And what we can do with a tree is take here some level, which is a distance delta times n from the root. And now note the following. The maximum at the bottom level, so mn, is greater than the minimum of SV, V in d delta n, plus the maximum over I equals from 1 up to 2 to the power n 1 minus delta of, so this is S, maybe I should, yes, and this should be, and here you have the maximum, so m n 1 minus delta I. And those are independent. So let me explain. The global maximum here is certainly larger than you look for the maximum of the maximum of these subtrees, and you add to it the minimum at this level. Okay? Then this is certainly a lower bound for the total maximum. But you see, this quantity we already control from below, because we already have an upper bound. So we already know that the maximum at this level is as a minimum at this level, which is a maximum of minus the object, which because of Gaussian is exactly the same as we started with. This is greater than minus some delta star n, some quantity that depends on delta times n, which will go to 0 with delta. These guys, on the other hand, are independent. And we have a probability that depends on epsilon to be larger than, so each one is larger than n times 1 minus delta times 1 minus epsilon with probability e to the minus c of epsilon n. That was our second moment computation. So if I choose my delta to be larger than epsilon, still eventually going to 0, but larger than epsilon, one of them will, now we have really independent, truly independent model. So we can do the computation for the independent case that we did in the beginning, and one of these guys is going to be larger than that with overwhelming probability. So the total will be larger than n times 1 minus delta 1 minus epsilon minus delta star n with high probability. And now I'm done, because I can take epsilon to 0 followed by delta to 0, and we will get the law of large numbers. Okay? So I want to emphasize in this computation just two things. The first is that we needed, the key was to do a variance reduction step, which is to identify what is the behavior of the vertex that is going to be close to the high value, and stick it into the computation of the second moment. And the second step is to do a truncation using the tree structure. Okay. Are there questions about this? Yes?
Just a verification, can we use the Slavian's lemma here?
Yes, but again, okay. So you can use, there are two parts to the answer. The first one is that if you use Slavian's lemma, you still need to compute the expectation of the maximum. Slavian lemma will not help you in computing the expectation of the maximum, in particular a lower bound on the expectation. So this you have to do somehow. Okay, and if you try to do it, you'll discover you need some argument like that. So it doesn't really help. Slavian lemma will play a very important role later. But here I said all the time the word Gaussian, but you realize I never really needed the assumption of Gaussian here. It was not a Gaussian computation. I used large deviations, and I used Varadan-Mogulski, so it's really not at the level of Gaussian computations. And so I wanted to emphasize that aspect, that's why. We will see Slavian, actually, we will see later Slavian's lemma coming up in different disguises, but right now it doesn't really help. Okay, other questions about this computation? Good. So, having done that, by the way, I should stop at 10:30, right? When should I stop? 10:45. Ah, okay, good, even better. So now our next goal is to discuss fluctuations and corrections. By corrections, I mean corrections to the mean. And I want to introduce an argument which is due originally in this context to Decking and Host. And in fact, Decking and Host treated the following case. So they looked at a general Galton-Watson, but again, we are simplifying everything. Maybe I should have made the comment. If you note, this computation would work also for Galton-Watson. There is nothing, the first moment, second moment, you could do also for Galton-Watson. We never really needed to know that the number of particles is 2 to the n. We only needed that the expectation of the number of particles is 2 to the n, and the expectation of a certain configuration, which is the particles splitting at a point, is what it should be. So that would hold also for Galton-Watson. Decking and Host considered the case of, say, a binary tree, but bounded increments. And what they proved is theorem. So I think it's 91. So actually I should have put some years here. So this is 66 and this is 70 plus. And I think 4 or 5. So just one word about that. So this theorem is not really explicit in Varadan's paper, but if you read it carefully, it's there. Mogulski, I think, is the first who actually wrote down the theorem explicitly. Okay, so what did Decking and Host do? They assumed bounded increments, and they showed that Mn minus the expectation of Mn is of order 1. In fact, their argument shows this precise statement. So there exists a C such that this is true for all n. Okay, so let me give the proof of the result. So the first step is the important step, is the following. We have our tree. Let's cut the tree after one generation. So this is one generation. We have 2 children. So we get the following recursion. Mn plus 1, so if this depth is n plus 1, this is equal to the maximum of Mn plus g, Mn plus g prime. So let me explain. Mn is just the maximum over this subtree. So you just look at this subtree of depth n, you add to it the first generation. Okay? So that's the maximum of the left branch of the tree. Mn prime plus g prime is just the maximum of this tree plus the g prime here. So really I should write g prime, g, and then everything will be clear. And of course, Mn plus 1 is a maximum of these 2 independent random variables. Okay? Now, before I continue with our argument, I want to write down here a small lemma. A small, very general lemma. Suppose that xv and yv are independent zero mean random fields. So by this I mean they are collection of random variable indexed by V. So this is a collection of random variable. This is a collection of random variables. So we have two such collections that are independent between themselves. It doesn't mean that xv is independent of xv prime. Just that these two collections are independent. That's all. Then the expectation of the maximum of xv plus yv is greater than the expectation of the maximum of xv. Okay, so the maximum is over v in some collection. And this collection, for the purpose of our discussion, let's take it finite. Okay, so this is a claim. And the proof is trivial. So let's do the proof. Let x star or x hat be such Okay, let's look at the index that achieves the maximum. If there are several, just choose one of them. Since everything here is finite, I really can define it without any difficulty. And now, of course, the expectation of the maximum of xv plus yv, this is certainly greater than or equal to the expectation of xv star v hat plus yv hat, because this is a maximum over all vertices. But by linearity of expectation, this is the expectation of xv hat plus the expectation of yv hat. But the expectation of yv hat is 0, because the y field is independent of the x field. So this is 0, and this is the right-hand side. Okay? So we have this lemma. So now I'm going to apply this lemma here. So this is exactly the situation I have. If you think about it, what is written here, it's just the maximum of a collection of random variables. Here I have a sum of two collections. One collection is just the values of the increment in this bottom line. And then the other one is just the random variable, the random field that takes the value g on each of these vertices and g prime on each of these vertices. So these two are, of course, the g field is independent of this field. So we can apply the lemma. And what we get is that the expectation of mn plus 1 is greater than or equal to the expectation of the maximum of mn and mn prime. I want to get rid of the g. So that's the first step. In particular, already from here, you see that the expectation of mn is increasing. Right? Because the maximum is certainly larger than one of them. And now comes the main trick of the proof, which is to say that the maximum of a and b is equal to a plus b plus the difference over 2. So let's substitute it here. And what will we get? We'll get that the expectation of mn plus 1 is greater than or equal to the expectation of mn plus the expectation of mn minus mn prime over 2. Where mn and mn prime is an independent copy of mn. So what we get is that the expectation of mn plus 1 minus the expectation of mn is greater than the expectation of mn minus mn prime, and we have a 2 here. Okay? So far, this was completely general. I didn't use a boundedness at all. Okay? Where did Decking and Host use a boundedness? Well, remember, we have a tree of depths n plus 1. Now let's cut it at depths n, before we cut it at the top, at the first generation. Now let's cut it at generation n. Because of the assumption of boundedness, because of the assumption of bounded increment, we have that mn plus 1 is bounded by mn plus a constant. This is almost surely. This is because of bounded increment. Because if you look at the leader at generation n plus 1, the largest vertex, which is somewhere here, its parent was at most a distance c below it. So the difference is at most c. Okay? So this just comes from boundedness. Which means, in particular, that the object that is written here is bounded. So if you substitute this back into here, this is less than 2c. So the conclusion is that the expectation of mn minus mn prime is bounded by 2c. But now let's apply Jensen. Condition on mn and push the expectation inside. This is greater than the expectation of mn minus the expectation of mn prime, which is the same as the expectation of mn minus f. And we are done. So in particular, we showed that the sequence mn minus its mean is tight. Okay? So this means that fluctuations are of order 1. Okay? So this was a very soft argument that only assumed the boundedness of the increments. Didn't need any computation. But I want to make some important comments about this argument. So in particular, it certainly does not apply to the Gaussian case. Now, you might think it's a technical issue, but be careful. The important part was this almost sure domination. And this almost sure was obtained by arguing as follows. If you look at all the vertices, all the edges in the n plus first generation, all these edges are uniformly bounded. Therefore, I can bound them at once with some constant. And I didn't distinguish between the situation in which at this level I had just one particle near the maximum or all the particles were near the maxima. It didn't matter. But if at this level I had many particles near the maximum and my edges here were unbounded, then what would I conclude? That the maximum is jumping by a lot. Because no matter how light the tail is of this increment, if I have a number going to infinity of edges here, the maximum of them will go to infinity. So the largest edge here will go to infinity, and then this argument cannot work. So this argument as is doesn't work for the unbounded case. However, there are two observations to be made. The first observation is that if somehow you are able to control this expectation, this difference of expectations of the mean, then you immediately control the maximum. So forget about the second step. Forget about this step. Just stop the argument here. If you can control the left side, which is now a discussion of expectations, then you control the right side. So I come back to your question about Slepian's lemma. If you have a good lower bound on the expectation of Mn, and you have a good upper bound, and the difference between the lower bound and the upper bound is of order 1, which we have certainly not achieved, but in the argument we did. But if you can do that, then you automatically control the fluctuations. You don't need to discuss anything more about fluctuations. I mean, you can discuss. Then the natural question is what is the limit law and etc. But at least to know that fluctuations are bounded, you are done. Okay? So that's the first comment. The first comment is that EMN plus 1 minus EMN bounded by some constant C implies fluctuations are of order 1. And this is now true in complete generality. No matter what the assumptions you put, as long as you are on a tree, independent edges, you have that. The second comment is, we actually have already proved something. We have proved the law of large numbers. This we actually honestly did. So we already know that Mn divided by n converges to a constant, in fact, almost surely, but this is not so important. From our computation, in fact, we know that. Our computation would give that. So the estimates are good enough to give that. And because of that, we have the following two facts. We have that fact and the expectation of Mn plus 1 minus the expectation of Mn is positive. Right? This silly observation that the expectation of Mn was increasing. But these two facts together mean that you can find a subsequence nk, deterministic, depending only on the expectation, such that the expectation of Mnk plus 1 minus expectation of Mnk is bounded, say, by 2c. Why? Because if that were not true, then this cannot be true. Right? If no such subsequence exists, it means that eventually all these differences are larger than 2c, so the expectation of Mn divided by n should go to 2c and not to c. And therefore, on this subsequence, which is, I remind you, a deterministic subsequence, so we have that Mnk minus Emnk is of order 1. So the expectation of that is less than 2c, or 4c, whatever. Which means fluctuations of order 1. So this means that, and in fact, if you think about it for a second, if you replace this 2 by an arbitrary large integer, then you can make this nk of arbitrary high density. So you can push the density of nk to 1 by doing that. And by density, I just mean that nk divided by k is less than 1 plus delta. Okay? So we actually have a very good hint here. I can give you tightness over deterministic subsequences that are very dense, that are almost dense. Okay? And this leads one to expect that in fact you will have always tightness, which is a correct result. Note that to get that, again, we needed very few assumptions. We needed the law of large numbers. That's it. Nothing more than the law of large numbers. Okay. Questions about this Decking-Host argument. So this argument is very flexible, and it will apply also to Gaussian fields. So that's the reason why I'm emphasizing it. For branching random walk, you don't really need it in order to conclude whatever you want. Okay, so So actually maybe the third remark is we will show, so we will see that the expectation of Mn is nx star minus 1/2 x star log n plus order of 1. So we will work hard to prove that. But once we have that, this will imply that the expectation of Mn plus 1 minus the expectation of Mn is of order 1. Because when you go from n plus 1 to n, you pick up a constant here, x star. The difference here goes to 0, and this is order 1 anyway. And so we will have tightness. Okay? So that's our plan now. And this was actually achieved by Bramson in his PhD thesis. So this is a result. And now all that remains is to prove it. Okay. So strictly speaking, this is under Gaussian assumptions. But, so Bramson did it under Gaussian assumption. In fact, Bramson did it for branching Brownian motions, which is a continuous model of branching random walk. But you can replace the word Gaussian by good, where good means what I wrote before, and the whole proof goes through. So that will not be a problem. Okay, so, yes? A what? Oh, very good. Thank you. Yeah, I would have. Good, thanks a lot. So, I want to emphasize some things about this formula. The first thing to emphasize, as Pascal has just pointed out, is that the leading term we already know is the same for the branching random walk case and the independent case. When we did our independent computation, you remember it was the same x star. The x star was computed from a large deviation argument. The rate function at x star should be equal to log 2. That's how it was computed. So that the first moment balances. So at the level of the leading term, you do not distinguish between branching random walk and independent random walks. It's the same. However, maybe I should write it here, in the model of independent increments, what we had was this. This is what we had. And you see that the second order term is not the same in the two computations. One has 1/2, the other has 3/2. So in the second order term, you start to see the branching structure. And that maybe begs the answer, where did this 1/2 come from? So if you remember the computation, this 1/2 came from the fact that the probability of SV, roughly nx star, was e to the minus nx star square over 2 divided by n to the 1/2. This 1/2, we needed to compensate for it by shifting x logarithmically in order to kill the 2 to the power n exponent. That was essentially what was happening in the independent computation. So if you believe Bramson's result, somehow it means that you should replace this 1/2 by 3/2. It's the same result, except that the exponent became 3/2 and not 1/2. Okay? So how do you get 3/2? This probability is, it doesn't see whether you are branching random walk or independent random walks or anything like that. This probability is a truth. So how will this 1/2 become a 3/2 suddenly? And the answer is, of course, that remember our second moment computation. When we did the second moment computation, we had been able to push in extra information that helped us control the branching random walk. And this extra information had to do with the whole path of the random walk. So even the law of large number you couldn't get if you just looked at the end point. You needed to consider somehow the whole path. And so it's clear that if we are hoping to get anything like that, any argument we are going to make will have to consider the whole path of the walk. Okay? So that's what I am going to do. And in the last 5 minutes that I have, I want to do a preliminary. And this preliminary is classical, so I will not prove it, I will just write it down. So, and this comes under the name ballot theorem. So suppose that I have xi, which are IID, random variables, which have zero mean and unit variance. And also, I have that the probability, okay, just not to write too many assumptions, let's assume it has non-zero density. You don't need this assumption, and in my notes there is a weaker assumption, but okay. And now you define Sn to be the sum of xi. Okay, so that's our random walk. Then, for k of the CLT scale, the probability is that your endpoint is roughly like that, and this quantity is of the order of k plus 1 over n to the 3/2. Okay, so first of all, I promised you a 3/2, here it is. We don't know yet why it is related to the branching random walk problem, but at least it's a 3/2. Second, what does this, so let's take the easiest case where you take k equal to 0. So what is this? This is just a classical problem in which you start at 0, you end at n. So a typical random walk will do something like that. That's a typical random walk. But what I'm asking is the event that the random walk does this. So it's all the time negative. And the claim is that the probability of that is of the order 1 over n to the 3/2. So an easy way to see that, as I said, I'm not going to prove that. There is an article on the archive by Bruce Reed, Luigi Adario Berry. And Bruce Reed, and which has lots of ballot theorems of different type and at least sketches of proof, so you can look it up. Of course, this is classical. Now, why n to the 3/2? Well, you see, the probability that a random walk is positive for distance n is 1 over square root n. And now you have three events. First, you have to be positive for some time. You also have to end up being positive. So that gives you another factor 1 over square root n. And then these two random walks have to meet. And the probability of that is 1 over square root n. So this sounds like a joke, but actually you can do a proof based on that by just considering here, and considering what happens in the middle, and you'll get 1 over n to the 3/2. Okay? So this n to the 3/2 will somehow be translated eventually to this 3/2 if we can understand why this event that is written here, this event that is written here is relevant at all. Why do we need to have SI positive all the time, or SI positive all the time? Why is it related? And that's a very good point to stop with a little bit of suspense. So I'll stop here.